I'm a big believer in the use of AI for various aspects of chip design. Both, if you think about the chip design phases, there's like high-level architectural explorations, there's more automated synthesis of high-level designs into lower-level things, there's automating verification, and then there's automating placement and layout and routing. And so I've done some work on Alpha Chip as one example, helping with placement and routing.
Very great Nature paper, by the way.
Oh, thank you. And that's been really useful for a bunch of generations of TPUs that we've designed. And how do you think? And I've seen some really nice work from Nvidia on various kinds of gradient-based methods for placement and routing. So how do you think about the use of AI in the actual hardware design process? Do you think like tackling these different stages with different AI-based approaches is the right thing? Do you think a much more end-to-end thing is possible? How do you see this evolving?
So we're trying to use AI wherever we can in our design process, and there are a number of examples. So for example, every time we have a new semiconductor process, we have to port our standard cell library to it. It's about 2,500, 3,000 cells, and that used to take a team of 8 people about 10 months, so 80-person months. And then we developed a program based on reinforcement learning called NV-Cell. I think we're up to NV-Cell 2 or 3 now, and it's overnight on one GPU. And the results are actually better than the human designs. In measures of goodness of size of the cells and power dissipation, delay, it matches or exceeds the human design. So it's a huge productivity gain, and it eliminates an obstacle to moving to new processes, because now we can move cell libraries over very quickly. And then we have this program called Prefix RL, which applies reinforcement learning to a really age-old problem in computer design, which is where to put the look-ahead stages in a carry look-ahead chain. And this is a problem that's been studied since the 1950s. And this RL program goes at it like it was an Atari video game, and it puts something in here and it grades itself. And it's not trying to make the fastest adder; it's trying to make actually the adder that barely meets timing and is as small and low power as possible. And it comes up with totally bizarre designs that no human would ever come up with, but they're actually 20 or 30% better than the human designs by those metrics. And then at a more holistic stage, we've for a number of years have had a series of LLMs that we called Chip Nemo and Bug Nemo. And what we did is we took a generic LLM, and then we fine-tuned it by feeding it all of the design documents proprietary to Nvidia. So this is stuff you can't get outside the company. It's all of the RTL.
Hardware design docs.
Yeah, all of the RTL for every GPU ever designed at Nvidia.
Yep.
All of the architecture specs for those, all sorts of stuff. And now you have this LLM that's actually very smart about GPU design. And one of the biggest gains of this is when you have a junior designer, it turns out the senior designers spend an enormous amount of their time explaining to the junior designers simple things like, how does a texture unit work? And particularly this texture unit. And now they don't have to ask the senior designers that. They can ask Chip Nemo that, and Chip Nemo will explain to them in great detail how the texture unit works. They have a follow-up question that will answer the follow-up question. So it improves productivity that way.
It's a very patient mentor.
Yeah. And the same thing when we have bugs, we can have it summarize bug reports and try to do attribution on bugs. Say, which module is this bug in? Who do we ARB? We always ARB somebody for a bug, action required by. And so we'll decide what designer gets ARBed for a particular bug. And then we're at the more exploration level, and particularly in NVIDIA research, we're now using agentic systems to try to do a bunch of thought experiments where we say, okay, here's a bunch of different ways we could go, figure out what this parameter space looks like, suggest new ways of doing things, run simple architecture experiments, and whittle the design space down to a smaller number of things that we can look at. We're trying to collapse the time. At NVIDIA, there's a stage when we're kind of done with the exploration effort that we have the F model. It's basically an executable model of the GPU to where we tape out the design. We have all the geometry done. It goes out to TSMC to make chips. And we'd like to collapse that space. And it turns out what the really long pole in that space is design verification. And so we're particularly looking at how we can use AI to prove that designs work more quickly. There are also a couple stages in there where we have to refactor the design, because we have, the RTL design is done, but then we've repartitioned things for floor planning, and now we have to move parts of the logic from one module to another and make sure everything still works. And those are the kind of things that I think we ought to be able to automate, and we should be able to collapse that time period down. But All that said, I'd love to have the end-to-end stage where I could simply say, design me the new GPU, and I'll go out skiing for a couple of days, and I'll come back, and it's done. But I think we're a long way from that. But I think it is making us much more productive.
Yeah, I mean, I think making every stage of that automated process fast enough that it can actually explore this enormous design space is super challenging.
And I think even when we get to the end-to-end, it's going to be sort of the master agent calling on these agents who are specialized in the different parts of that pipeline to carry out their parts, and then perhaps to iterate when it's not happy with the quality of the result.
Yeah, and potentially even split up in the same way we split up human chip design teams, where you have this agent focusing on this part of the chip, and then this one over here with some well-known interfaces between them, and then they have to negotiate changes to those
exactly.
interfaces.
They'll have the same kind of meetings we have, but between agents.
Yes. Interagency meetings.